Hello everyone, welcome back. My name is Naireza Alvin, alongside my Anja Janet, and we are presenting work about a machine learning based credit risk prediction tool that assesses the credit risk assessment process and also the loan approval process. So usually financial institutions or money lending institutions, they face revenue loss whenever they approve loans to bad customers. So they want to minimize loan defaults and maximize profitability in these institutions. So the traditional credit risk prediction models aren't widely used to solve this issue in Uganda because of their low accuracy. The low accuracy is attributed to their limited ability to capture complex patterns in high dimensional data for the borrowers. So these traditional credit risk prediction models that are machine learning based, they become less accurate, and so they aren't widely used in Uganda. Basically, to automate the credit risk assessment process and the loan approval process. So this work aims at combining advanced ML techniques so as to develop a credit risk prediction tool that is more robust and more accurate, so that it can be deployed in Uganda and used, and it can be able to operate in resource-restrained environments and improve the accuracy in the credit risk prediction process. So moving on, the related works to this, we have some of the works. These are some of the works that have been done because we are not building on this idea from nowhere. This is some of the work that has been done. Now, like the European Journal of Operational Research, these were basing on integrated graph representation learning with graph transformation. So now, as I've said, the limitation of the traditional credit risk prediction models that are relating to the work that has been done in this area, their ability to capture complex patterns in high dimensional data for borrowers is the main issue here. And high dimensional data, I've talked about it. Among the computational problems, another thing is imbalanced data sets, which makes it difficult to support both claims. And in this case, I find that most data sets for this, we have more borrowers who have defaulted, more borrowers who have complied than those who have defaulted, which can cause bias in predictions. Then also model complexity and efficiency, as these advanced ML tech models that we want to combine, they're computationally expensive to make those computations. They need huge resources, computational resources, and also to deploy them. Some of the such questions: what are the main comparative advantages of using these advanced techniques that you want to use over the traditional methods that have been used? Then how can the continuous feedback loop between the teacher and the student model, that is knowledge distillation, be optimized to ensure adaptive learning and improved prediction? And our objectives, first one, to design a model that overcomes the difficulty of the traditional models. I've talked about their limitation. Then also to develop a credit risk prediction model that can effectively operate in resource-restrained environments, not using huge computational resources. Then also to minimize overfitting and underfitting of these advanced techniques, as they always tend to overfit. So we have evaluated our proposed model, that is the ensembled model, against the existing traditional models, demonstrating its accuracy and computational efficiency. We also implemented advanced techniques, as we've listed them here. Then we also implemented techniques such as SMOT to handle largely imbalanced prediction datasets. This is the methodology. Basically, the flow of the assembled model. This is the image behind our idea. So we are combining advanced ML techniques. In this case, we have knowledge distillation, we have inverse reinforcement learning, we have deep Q learning to form one robust and more accurate credit risk prediction tool in a way that the teacher model learns through deep Q learning. It learns on the raw data. After learning, it has to generate soft labels. The soft labels are then distilled through knowledge distillation to the student model, which learns on basing on that knowledge that has been distilled, and makes predictions that are believed to be better than or more accurate than the teacher's predictions. After making those predictions, the student's model is supposed to send back the feedback to the teacher model through inverse reinforcement learning, so that it can be retrained basing on the feedback, and then it can improve. So the loop continues as the models continue to improve each other. I'll let my colleague pick it up from here. Thank you.
Hello, my name is Manja Janet, and I'll take you through our dataset description and exploratory data analysis. So we sourced our dataset from GitHub. It has those number of features and rows. And basically, that's an insight of how our dataset looks like. Some of the features we have: gender, education, loan status, and so on. So that's how it looked like. And here are some of the results and discussions from our exploratory data analysis. So as you can see, we have a pie chart for credit history distribution, and 1 stands for those who don't defaulted, and 0, those are the percentage of people who defaulted. We have here a scatter plot for applicant income versus loan amount. It shows the gender of people, where red stands for the males and most are males, and we have few females, and the applicant income most range from 0 to 20,000. Yes. Moving on, this is just the explainable AI results. This is a waterfall plot for a given instance, and as you can see, credit history as the most contributing feature to the predictions made by a certain model, and these are the sharp values. And as you go on, followed as the most contributing. So as you can see, using the log odds of predicting this borrower as a good borrower. We have applicant, this is a PDP for applicant income, and these are the average probabilities. And as you can see, the distribution is just as the applicant income increases, the probability of this borrower paying back a loan also increases. Let's go on. So these are some of the model results after training our models. And as you can see, we have graph neural networks. It had an accuracy of that, and it performed well across other metrics. And yeah, so this is our assembled model and how it performed. We have the teacher model. This is its accuracy, 0.94. And then the student model after knowledge distillation, this is how it performed. And then after the IRL feedback loop and retraining the teacher model, that's how it also performed. So some of the conclusions. So credit risk has evolved from basic credit scoring. So now we are using more robust techniques than the previous ones. And we believe our methodology performs more well than the traditional techniques. So some of the limitations we faced, and this work required huge computational resources for these advanced techniques and their deployment, and the highly imbalanced data sets, whereby you cannot support both claims equally, the default and no default. So our next steps, the future acts, we shall have an asked feature engineering, such that we can introduce more new features to train the models. Advanced data balancing, because we've so far only used SMOT, so we want to use more data balancing methods, and then we'd like to improve more on the user interface such that it become user-friendly to the users of this tool. So I'm going to give you a demonstration of our current deployment. So this is it. This is how the interface looks like. So you can just input different features in here. Number of dependents, the education, if the user is self-employed, the applicant income, the core applicant income, loan amount, the loan amount term, our credit history, and the property area of the applicant. Then you submit, and then it gives you a prediction. Yes, so thank you. That's what we had for you so far.